Hey there! Welcome back to Hoffy Sleep. I'm absolutely thrilled you clicked on this video today because we're about to embark on one of the most mind-bending journeys through the very fabric of reality itself. I was sitting on my couch last night, just staring at my coffee getting cold, like we all do, and it hit me. That coffee will never, ever get hot again on its own. Never. Not in a million years, not in a trillion years. Not until the very last star flickers out. And that simple, everyday moment, that cup of coffee cooling down on your table, is actually a window into the deepest mystery of the universe. Why does time only move forward? Why can't we unbreak eggs? Why can't we unspill milk? Why can't we go back and fix that awkward thing we said at a party 3 years ago? Well, okay, that last one might be more about social anxiety than physics, but you get my point. Before we dive into the cosmic soup of entropy, the Big Bang, and the very nature of reality itself, do me a quick favor. If you're enjoying this content, if you want more deep dives like this where we take complex ideas and make them as easy as understanding why your phone battery dies, then smash that like button. It tells YouTube that this is the good stuff, the stuff that makes you think. And it helps other curious minds like yours find this channel. And while you're at it, hit that subscribe button with the notification bell because we've got some incredible videos coming up that will completely change how you see the world around you. And here's something fun. I want to hear from you. Drop a comment below and tell me where you're watching from and what time it is right now. I'm genuinely curious. Are you watching this at 3 a.m. in New York because you can't sleep and you're deep in a YouTube rabbit hole? Is it noon in Tokyo on your lunch break? Maybe you're in a small town in India I've never heard of, or on a train somewhere in Europe. I read every single comment, and there's something magical about picturing all of us around the world, different time zones, different lives, all united by this one question about time itself. So seriously, let me know. Now, let's talk about that cup of coffee. Imagine you're watching the steam rise from it right now. Those little water molecules are dancing around, carrying heat away into the air. If you could zoom in with a microscope powerful enough to see individual atoms, which, by the way, would be the most powerful microscope in the history of humanity, you'd see something fascinating. You'd see those coffee molecules, hot and energetic, bouncing around like toddlers hopped up on sugar, colliding with the cooler air molecules, which are moving more like, well, adults at a yoga class. Every time they collide, they share a tiny bit of that energy. The hot molecules slow down a smidge, and the air molecules speed up a smidge. And this happens again and again and again, billions of times per second, until, eventually, your coffee is the same temperature as the room. And here's the kicker. This process never, ever goes the other way. The room never gets colder while your coffee spontaneously heats up. The energy never flows from the cold air into the hot coffee and makes it hotter. Why not? The laws of physics, at their most fundamental level, are reversible. If you look at the equations that describe how a single atom moves, they work perfectly fine backwards. The math doesn't care about time. Run the equation forward, the atom moves one way. Run it backward, it moves the other way. The equation is just as happy, just as valid. So why, when we put lots and lots of atoms together, like the billions and trillions in your coffee, does time suddenly develop a direction? Why does it pick a side and stick with it? This is what physicists call the arrow of time. And it's not just one arrow, it's a whole quiver of arrows, all pointing the same way, and nobody knows why they all agree. It's like there's a cosmic conspiracy, a universal vote that happened at the beginning of everything, and the result was time goes forward. End of story. But that's not good enough for us, is it? We're curious creatures, we humans. We want to know the why. Why forward? Why not backward? Why not sideways? Why is the past different from the future? And to understand this, we need to go on a journey that starts with your coffee, travels through the steam engines of the Industrial Revolution, rockets past the birth of the universe itself, and ends, well, it ends with us, right here, right now, trying to make sense of it all. So let's start simple, really simple. Imagine you have a box, and inside this box you put a bunch of gas molecules, let's say 100 of them. Now let's say you put all 100 of them in one corner of the box. You squeeze them in there, maybe with a little partition, and then you remove the partition. What happens? Of course, they spread out. They fill the box. They don't stay huddled in the corner like shy kids at a school dance. They explore. They distribute themselves evenly throughout the available space. And once they're spread out, they stay spread out. They don't spontaneously reassemble in the corner. Why? Well, you might say, duh, that's just how things work. But physics is never satisfied with duh. Physics wants numbers. Physics wants probabilities. So let's get numerical about this. There is exactly one way, well, technically many ways, but let's keep it simple. There's essentially one configuration where all the molecules are in that corner. But there are a gazillion ways for them to be spread out throughout the box. And when I say gazillion, I'm not exaggerating. The number of ways to arrange those molecules in the larger space is astronomically larger. It's like comparing a single grain of sand to all the sand on all the beaches on Earth. Actually, it's much, much worse than that. It's like comparing a single atom in that grain of sand to all the atoms in the entire observable universe. The difference is that massive. So if you imagine the molecules just jiggling around randomly, bouncing off each other, bouncing off the walls, they're going to explore all these possible arrangements. And purely by chance, by random motion, they're vastly, overwhelmingly more likely to be in one of the spread-out configurations than in the one special corner configuration. It's not impossible that they'd all end up back in the corner. It's just so unbelievably unlikely that you could wait for the entire age of the universe multiplied by a trillion times, and it still probably wouldn't happen. That's the first clue to our mystery. Time's arrow seems to point in the direction of increasing probability. But we need to go deeper. That word probability is hiding something profound. It's hiding a concept that will change how you see everything. Entropy. Now, don't run away. I know entropy sounds like one of those scary physics words that makes people think they need a PhD to understand it. But you don't. It's actually incredibly simple. Entropy is just a measure of how many ways you can arrange the microscopic parts of something, its atoms, its molecules, while keeping its macroscopic properties the same. That's it. That's the whole definition. When your coffee is hot, there's only a few ways to arrange the molecules so that the coffee is that specific temperature and the air is that specific temperature. When the coffee cools down and the air warms up a bit, there are vastly more ways to arrange the molecules to achieve that new state. So, entropy has increased. The system has gone from a special ordered low probability state to a common disordered high probability state. And this is the second law of thermodynamics, which isn't really a law in the same way that gravity pulls things down is a law. It's more of a statistical principle, a law of probability. In a closed system, entropy always increases. Or at least it almost always increases. It never decreases. And that never is the arrow of time. Let's pause here for a second, because this is a good spot to think about what we're really saying. We're saying that the reason you can remember yesterday but not tomorrow, the reason you were born, grew older, and will eventually die, the reason the universe had a beginning and will have an end, isn't because of some fundamental rule written into the fabric of space-time. It might just be because there are more ways to be disordered than ordered. It's a statement of statistics. It's about counting. It's about the fact that there are more ways to be messy than tidy. Think about your bedroom. How many ways can you arrange your clothes, your books, your random stuff so that it's perfectly clean? Everything in its place, folded, organized. There's maybe a handful of clean configurations. But how many ways can you arrange everything so that it's a mess? Clothes on the floor, books scattered, that one chair that somehow collects everything. There are millions of messy configurations. So, if you just live your life moving things around randomly, you're naturally going to drift towards messiness. It's not a law of the universe that rooms get messy, it's just statistics. And the universe, it turns out, is just a very, very big room that started off improbably clean.
Now, here's where things get really interesting. If entropy always increases, and if entropy defines the arrow of time, then the universe must have started in a very, very special, very, very low entropy state. It must have been born in an incredibly ordered configuration. And it did. We call that moment the Big Bang. Picture this. 13.8 billion years ago, the entire observable universe, all the galaxies, all the stars, all the planets, all the coffee cups, everything, was compressed into a space smaller than an atom. Can you even imagine that? That's not just small, that's mind-bendingly ridiculously small. And it wasn't just small, it was smooth, incredibly smooth, the most uniform thing you can imagine. The density was almost exactly the same everywhere, to something like 1 part in 100,000. That's like having a beach where the tallest sandcastle is only a fraction of a millimeter higher than the lowest dip. It's absurdly flat, absurdly uniform. And that uniformity, that smoothness, is a very low entropy state. It's highly ordered. It's like having all the gas molecules in the corner of the box, except the box is the entire universe and the corner is a single point. From that moment of perfect order, the universe has been unwinding, expanding, spreading out, getting more disordered. The expansion of space itself is creating more room for things to get messy. It's like blowing up a balloon while simultaneously shaking it full of confetti. The confetti has more and more space to explore, more ways to be disordered. This is the cosmological arrow of time, and it's deeply connected to the thermodynamic arrow of time. They're probably the same arrow, just viewed from different angles. The universe expands, entropy increases, time moves forward. But why did it start so ordered? Why was the Big Bang such a special low-entropy moment? This is where physics gets speculative because we don't have a definitive answer, but we have some incredibly compelling ideas, and we're going to explore every single one of them in excruciating detail, because that's what you signed up for when you clicked on a video about the arrow of time. Let's talk about what we mean by low entropy at the Big Bang. Imagine you have a deck of cards, fresh out of the box. It's perfectly ordered. Ace of spades, 2 of spades, 3 of spades, all the way up to the King of Hearts. That's one specific order. There are 52 factorial ways to arrange a deck of cards. That's 52 times 51 times 50, all the way down to 1. That number is huge. It's 8 times 10 to the 67th. That's an 8 followed by 67 zeros. If you shuffled that deck randomly, the chance of it returning to its original order is 1 in 8 times 10 to the 67th. You could shuffle for the entire age of the universe 1,000,000 times per second, and you'd never, ever see that original order again. The Big Bang was like that deck of cards, but the deck had something like 10 to the 80 cards, and they were all in perfect order. The number of ways they could have been arranged in that smooth, uniform state is incomprehensibly tiny compared to the number of ways they could have been arranged in a messy, clumpy, high-entropy state. So the universe started in the most improbable configuration possible, and it's been getting more probable ever since. But why? Why did it start that way? This question haunted Einstein. It haunted Boltzmann, who pioneered statistical mechanics and eventually died by suicide, partly because his ideas about entropy were so controversial and misunderstood in his time. It's haunted every great physicist since. And the answer might lie in something called the past hypothesis. This is a philosophical and physical assumption that the universe started in a low-entropy state. It's not derived from any deeper principle, at least not yet. It's an initial condition. It's a fact about the beginning of time that we have to accept, and from it, everything else follows. The past hypothesis says the universe started with very low entropy. That's it. That's the whole thing. And from that single assumption, we can derive the second law of thermodynamics. We can explain why ice melts, why fires burn, why we remember the past and not the future. But it feels like cheating, doesn't it? It feels like we just moved the mystery back one step. Instead of asking why does entropy increase, we ask why did the universe start with low entropy? And that's an even bigger mystery. Now let's explore some possible answers to this deeper question. One possibility is that the low entropy beginning is just a brute fact. It is what it is. There's no deeper reason. The universe could have started in any state, and we just happen to be in the one that started low entropy, because if it hadn't, we wouldn't be here to ask the question. This is called an anthropic argument. It says that the conditions necessary for life, like stars, planets, chemistry, all of which require a low entropy beginning, are only possible in universes that started with low entropy. So, of course, we find ourselves in such a universe because we couldn't find ourselves in any other. It's a bit of a philosophical cheat, but it might be true. It might be that there are many, many universes, most of them dead, boring, featureless expanses of uniform goo, and we just happen to be in the interesting one. This is the multiverse hypothesis, and it's gotten a lot of traction in modern cosmology. But we're not going to just hand-wave it away. We're going to dig into what that would actually mean. Imagine a vast cosmic landscape, a multiverse, where universes are constantly being born, inflating like bubbles in a boiling pot of water. Each bubble universe has its own laws of physics, its own initial conditions, its own entropy. Most of these bubbles are dead on arrival. They're born in high-entropy states, just uniform mush, no structure, no stars, no planets, no life. But a tiny, tiny fraction, maybe one in a googolplex, are born in low-entropy states. Those are the ones where interesting things happen. Those are the ones where galaxies form, stars ignite, planets coalesce, and eventually creatures evolve who can look up at the sky and ask, why does time only move forward? So we exist because we can only exist in a low-entropy universe. The fact that we're here asking the question selects for a low-entropy beginning. It's not that the low-entropy beginning is special, it's that we're special and we're biased. We can only observe the kind of universe that allows observers. But let's not settle for that. Let's get more creative. Another possibility is that time itself is an emergent phenomenon. Maybe at the most fundamental level, there is no time. There's just a static, timeless reality, and time is something that arises from the way we piece together our experiences. This is a radical idea, but it's taken seriously by physicists like Julian Barber and others who work on quantum gravity. They suggest that the universe is a collection of snapshots, static moments, and our consciousness stitches them together into a flowing narrative. The arrow of time in this view isn't a property of the universe, it's a property of our perception. We perceive time as moving forward because of the way our brains process information, because of memory, because of cause and effect. But the underlying reality is timeless. It's a block universe where past, present, and future all exist equally, and we're just moving through it like a reader flipping pages in a book. The book is static, the reading is dynamic. Let's explore that idea more because it's a doozy. The block universe comes from Einstein's theory of relativity. In relativity, space and time are woven together into a four-dimensional fabric called space-time. And just as all of space exists at once, all the points from here to the edge of the universe, so too does all of time. The past doesn't cease to exist, it just is in a different region of space-time. The future doesn't not yet exist, it's already there. We just can't see it yet, the same way we can't see what's around the corner of a building until we walk there. So in this view, the question, why does time move forward, is like asking, why do we walk forward instead of backward? Well, we could walk backward if we wanted to. There's no law of physics preventing it. But we don't because it's impractical, because our eyes face forward, because our bodies are built for forward motion. Similarly, maybe our consciousness is built to experience time in one direction, even though the universe itself doesn't have a preferred direction. But here's the problem. With that, if the universe is truly timeless and static, why do we see entropy increasing? Why is there any asymmetry at all? If everything just is, why is there this apparent gradient from low entropy to high entropy? The answer might be that the low entropy beginning is just a special boundary condition in this static block. It's like having a book where the first page is very ordered and the last page is very disordered, and all the pages in between show a gradual progression. The book itself doesn't change, it's just structured that way. So the arrow of time is built into the geometry of space-time. It's not that time flows, it's that the universe is structured with an entropy gradient, and we experience that gradient as the flow of time.
But wait, I'm getting ahead of myself. Let's go back to basics for a moment and really understand entropy, because everything else rests on this foundation. I want you to imagine a sand castle. You build it on the beach, with towers and walls and little windows. It's a highly ordered structure. It has low entropy because there are very few ways to arrange those grains of sand to make that specific castle. Now the tide comes in. Wave after wave washes over it. The castle crumbles. The grains scatter. They become part of the random, chaotic beach. The entropy has increased. The sand is now in a high entropy state. But here's a thought. If you filmed this process and played it backward, you'd see the waves retreat
the sand grains spontaneously assembling themselves into a castle, the water pulling away. And you would immediately know the film was running backward. Why? Because it's absurdly improbable. But, and this is crucial, it's not impossible. If you had a beach with trillions of grains of sand being tossed around by waves for trillions of years, eventually, purely by random chance, you might see them spontaneously form a sandcastle. It would be a miracle of probability, a cosmic fluke, but it's not zero. So, entropy increase is not a fundamental law, it's a statistical tendency. It's just that the tendency is so overwhelmingly strong that, for all practical purposes, it might as well be a law. Now, let's connect this to information, because entropy and information are two sides of the same coin. Imagine you have a hard drive. When it's empty, it's in a high entropy state. The bits can be anything, zeros or ones, randomly distributed. When you fill it with a movie, you're imposing order. You're creating a low entropy state where the bits are arranged in a very specific way to encode that movie. But to do that, you have to do work. You have to use energy. And using energy always increases entropy somewhere else. Your computer heats up. The power plant burns fuel. The universe as a whole gets more disordered. So, information is inherently linked to entropy. The more information you have about a system, the lower its entropy. The less information, the more uncertain you are about its microscopic details, the higher its entropy. This is why the second law is sometimes called the forgetting law. As entropy increases, information about the precise state of the universe is lost. We lose track of the details. The universe becomes more generic, more featureless, more boring. Let's think about this in terms of our own memories. Your brain is a fantastically ordered system. It's a low-entropy island in a high-entropy universe. The memories you have, your first kiss, the taste of your favorite food, the face of your mother, these are highly specific configurations of neurons and synapses. They represent information. They represent order. But to create and maintain those memories, your brain has to consume energy. It has to increase entropy. It has to burn glucose, release heat, contribute to the overall disorder of the universe. So, your ability to remember the past is directly tied to the thermodynamic arrow of time. You can remember the past because the past had lower entropy. You can't remember the future because the future hasn't happened yet, and it will have higher entropy. Memory is an entropy gradient detector. It's a device that takes advantage of the fact that the past is ordered and the future is disordered. But wait, why do we experience this gradient as a flow? Why does it feel like time is moving? This brings us to the psychological arrow of time. There's a famous physicist named John Wheeler who once said that time is what prevents everything from happening at once. And there's truth to that. Our consciousness seems to take in information, processing it, and storing it as memories. This process is inherently sequential. You can't have a memory of a future event that hasn't been processed yet. So, the direction of information processing, from input to processing to memory, defines our subjective experience of time's arrow. We feel time moving forward because our brains are constantly creating new memories, and those memories accumulate in the direction of increasing entropy. We're like boats sailing downstream on the river of entropy, and we call the direction we're sailing the future. Now, I want to address a common confusion here because it's important. Some people hear entropy increases and think it means disorder increases in the everyday sense. But that's not quite right. Entropy is about the number of microstates corresponding to a macrostate. Sometimes what we perceive as order can actually be high entropy, and what we perceive as disorder can be low entropy. For example, imagine a galaxy. It looks ordered, a beautiful spiral, swirling stars, but actually that's a high entropy state compared to the early universe. The early universe was smooth and uniform. A galaxy is clumpy, structured, full of gradients and differences. But those gradients allow for interesting things like stars, planets, and life. So, entropy increase doesn't necessarily mean things get less structured in a visual sense. It means they get more probable, more generic, less special. And life, interestingly, is a kind of intermediate entropy state. We're not as ordered as the Big Bang, but we're far more ordered than the eventual heat death of the universe. Speaking of heat death, let's talk about where this is all heading. If entropy keeps increasing, and there's no reason to think it won't, the universe will eventually reach a state of maximum entropy. This is called the heat death of the universe. It won't be hot, it'll be cold, dark, and uniform. All the stars will have burned out, all the black holes will have evaporated through Hawking radiation, all the matter will have decayed. The universe will be a thin soup of particles, photons, and maybe some other stuff, all at the same temperature, spread out over an unimaginably vast expanse. There will be no gradients, no differences, no fuel for processes that increase entropy further. Time's arrow will still point forward, technically, but there will be nothing to experience it. No life, no thought, no memory. It will be a timeless, featureless void. The universe will have forgotten itself. And this is the ultimate destiny that the arrow of time is pointing towards. It's not a happy ending, but it's the logical conclusion of the second law. But, and this is crucial, here's a twist. If the universe reaches maximum entropy and it's all uniform, could it then fluctuate back to a low entropy state? This is where we get into some really wild territory. There's a concept called a Boltzmann brain. Picture this. In a universe that has reached heat death, where everything is uniform, there will still be random fluctuations. Particles will occasionally, by pure chance, come together in weird configurations. Most of the time, they'll just form random blobs of particles. But very, very, very rarely, they'll form a brain, a fully functioning brain, with memories, thoughts, and the illusion of a surrounding universe. This is a Boltzmann brain. And here's the terrifying part. In an eternal high-entropy universe, Boltzmann brains would be vastly more common than real observers like us, who evolved slowly over billions of years in a low-entropy cosmos. So, if the universe is eternal and infinite, you're more likely to be a Boltzmann brain, a fleeting random fluctuation in a void, than a real person in a real universe. This is called the Boltzmann problem, and it's a major challenge for cosmological models that invoke eternal inflation or infinite time.
But don't panic. There's a way out. If the universe had a beginning, a true finite beginning like the Big Bang, and if it's not infinite in time, then Boltzmann brains aren't a problem. We're real. We're not random fluctuations. We're the product of a genuine low-entropy beginning. So, the arrow of time isn't just a curiosity. It's what makes us possible. It's what makes reality real, as opposed to a random hallucination in a void. Let's get back to the nuts and bolts. How exactly does entropy increase? What are the mechanisms? Well, it's all about diffusion, radiation, and the expansion of space. When your coffee cools, the heat energy diffuses into the air. The hot molecules share their energy with the cold molecules. This is thermal contact. If you have a hot object and a cold object touching, energy flows from hot to cold until they're the same temperature. It never flows the other way. Why? Because energy is conserved, this is the first law of thermodynamics, but it spreads out. It becomes less useful. The technical term for useful energy is free energy, or exergy. When you have a temperature difference, you can do work. You can run a heat engine. You can power a civilization. But as the temperatures equalize, that free energy disappears. It becomes bound energy, useless for doing work. So entropy increase is really about the degradation of energy. The universe is constantly turning useful energy into useless energy. Stars burn hydrogen, creating heat and light. But that heat and light spreads out into space and becomes useless. Eventually, all the hydrogen will be gone, all the stars will be dark, and the universe will be a graveyard of cold, dead matter. Now, let's talk about black holes, because they're absolutely fascinating in the context of entropy. For a long time, physicists thought black holes were the ultimate endpoints of entropy. They seemed to be perfect absorbers, swallowing everything, destroying information, creating a paradox. But then, Jacob Bekenstein and Stephen Hawking came along and changed everything. Hawking discovered that black holes aren't perfectly black. They emit radiation, Hawking radiation, because of quantum effects near the event horizon. And this radiation has a temperature. And if something has a temperature, it has entropy. In fact, black holes have enormous entropy, proportional to the area of their event horizon. This is the Bekenstein-Hawking entropy formula, and it's one of the most profound equations in physics. It says that the entropy of a black hole is the maximum possible entropy for a region of space. If you take any volume of space, the most entropy you can cram into it is if you turn it into a black hole. So black holes aren't the end of entropy, they're the peak of it. They're the ultimate high-entropy objects. But here's the weird part. When a black hole evaporates through Hawking radiation, it seems to lose information. The radiation is thermal, random. It doesn't seem to carry any information about what fell into the black hole. If you throw a library into a black hole and the black hole evaporates, you just get random photons. Where did the information go? This is the black hole information paradox, and it's one of the biggest unsolved problems in theoretical physics. Some physicists think the information is preserved in subtle correlations between the Hawking photons. Others think it's stored in a holographic boundary at the event horizon. Some even think it escapes to a parallel universe through a wormhole. The truth is, we don't know. But whatever the answer is, it's deeply connected to entropy and time. Because if information is lost, then entropy can decrease, and the arrow of time could reverse. But if information is preserved, then entropy always increases, and the arrow is unbreakable. Let's step back and think about the Big Bang again. We said it was smooth and uniform, which is low entropy. But why was it smooth? In the 1980s, a physicist named Alan Guth proposed a theory called inflation. Inflation says that in the first tiny fraction of a second after the Big Bang, something like 10 to the negative 36th seconds, the universe expanded exponentially. It doubled in size again and again and again, maybe 100 times. This inflation stretched out any initial irregularities, any wrinkles or bumps, and made the universe incredibly flat and uniform. It also created the seeds of structure. Tiny quantum fluctuations, little jitters in the fabric of spacetime, were stretched to cosmic scales, and these became the density variations that eventually grew into galaxies and stars. So inflation explains the smoothness of the early universe, which gives us the low entropy initial condition. But it also raises a question. What came before inflation? Was there a pre-inflationary universe? Was it high entropy? Did inflation somehow reset the entropy clock? There are several possibilities. One is that the universe before inflation was in a high entropy state, but inflation created a region of low entropy, a bubble, within that high entropy background. This is like having a hot, chaotic universe, and then a fluctuation creates a small, ordered patch that expands. But this runs into the Boltzmann brain problem again. If the pre-inflationary universe is eternal and high entropy, then random fluctuations would create low entropy bubbles all the time, but they'd be vastly outnumbered by random fluctuations that just create brains. So inflation needs a beginning too. It needs a starting point. Some theories suggest that inflation is eternal, creating an infinite multiverse of bubble universes, each with its own laws of physics. But then we're back to the anthropic principle. We live in a bubble that started with low entropy because that's the only kind of bubble that allows for observers. Another possibility is that the universe is cyclical. Maybe it goes through endless cycles of Big Bang, expansion, contraction, Big Crunch, and then another Big Bang. In these cyclical models, entropy increases from cycle to cycle, but each new cycle starts fresh with low entropy, somehow. The question is, how? How does the universe reset? Some theories propose that the contraction phase doesn't exactly mirror the expansion phase. There's a bounce where entropy is somehow dumped into a new dimension, or dissipated, or reset by some unknown physics near the singularity. But this is highly speculative. There's no evidence for a cyclical universe, and many physicists think it's mathematically inconsistent with the second law.
Let's talk about quantum mechanics, because this is where things get really weird. In quantum mechanics, the fundamental equations, like the Schrödinger equation, are perfectly time reversible. If you replace t with negative t, the equation still works. So at the quantum level, there's no arrow of time. But when we make a measurement, something strange happens. The wave function, which describes all the possible states a particle can be in, collapses to a single state. This collapse appears to be irreversible. Once you've measured a particle's position, you can't unmeasure it. The information about the other possible positions is lost, or at least it's inaccessible to you. This is the measurement problem, and it's deeply connected to the arrow of time. Some interpretations of quantum mechanics, like the Copenhagen interpretation, say that measurement is a special process that breaks time symmetry. Others, like the many worlds interpretation, say that measurement doesn't collapse the wave function. Instead, it branches the universe. All possible outcomes happen, but in different branches. In this view, time's arrow is about which branch we find ourselves in. We experience one branch where entropy increases, but there are other branches where entropy decreases, and other versions of us experience time backwards. But we can't communicate with them. So, from our perspective, the arrow is fixed.
There's also the concept of decoherence. When a quantum system interacts with its environment, it loses its quantum properties. It becomes classical. This process is irreversible. The information leaks into the environment, and you can't get it back. So decoherence creates a quantum arrow of time. But decoherence itself is a consequence of entropy. The environment is a high-entropy system, and when the quantum system interacts with it, the system inherits that entropy. So the quantum arrow is really just the thermodynamic arrow in disguise. Let's think about causality. We think of cause and effect as fundamental. The cue ball hits the 8-ball, and the 8-ball moves. Cause precedes effect. But is that a fundamental law, or is it emergent? In physics, the equations don't have a cause and effect label. They just relate events. The asymmetry comes from the fact that we can control causes but not effects. You can choose to hit the cue ball, but you can't choose to make the 8-ball move and have that cause the cue ball to be hit. This is because causes are in the past, which we can affect, while effects are in the future, which we can't. But why can't we affect the future? Because of entropy. The future is uncertain, high entropy, many possibilities. The past is fixed, low entropy, a single reality. So causality is also an arrow of time, and it's also derived from entropy. Now let's get really philosophical for a moment. What would it mean for time to go backward? If you reversed the arrow of time, would you notice? Would your memories flow from future to past? Would you experience things in reverse? This is the plot of many science fiction stories, but it's worth thinking about seriously. If the arrow of time reversed, entropy would decrease. Your coffee would get hotter, ice would unmelt, broken eggs would reassemble. But here's the thing. Your brain is part of the physical system. If entropy decreased, your brain would also run backward. Your memories would be erased as you unexperienced events, so you wouldn't remember the future any more than you remember the actual future. From your perspective, the reversed time would feel just like normal time. You'd have memories of what we call the future, and you'd be confused about what we call the past. The arrow of time is self-consistent. Whichever direction it points, that's the direction we call forward. So the question, why does time only move forward, might be tautological. It moves forward because we define forward as the direction it moves. But that feels unsatisfying. We want to know why there's an arrow at all, not just why we label it one way. And the answer, as we've seen, is entropy. But entropy is a statistical concept. It depends on how you coarse-grain the universe, how much detail you ignore. If you knew the exact position and velocity of every particle in the universe, you'd have complete information, and entropy would be zero. The universe would be perfectly described. But we don't have that information. We can't have that information. So we use probability. We talk about macro states, things like temperature, pressure, volume, and we ignore the micro states. The arrow of time emerges from this ignorance. It's a feature of our description, not necessarily a feature of reality itself. But it's a very robust feature. It's not like we could just choose to describe things differently and make the arrow disappear. The arrow is objective in the sense that any observer who coarse-grains the universe in a reasonable way will see entropy increasing. Let's talk about the initial conditions problem again, because it's so central. The Big Bang was a low entropy state, but why? One radical idea is that the universe didn't have a beginning at all. Maybe time is infinite in both directions, but the entropy gradient is local. Maybe our observable universe is just a statistical fluctuation in an eternal high-entropy cosmos. This is the Boltzmann universe idea. In an infinite amount of time, anything that can happen will happen, including a fluctuation that creates a universe that looks exactly like ours, with all our memories, all our history, all our evidence of a Big Bang. But as we discussed, this leads to the Boltzmann brain problem. If our universe is a random fluctuation, it's far more likely to be a tiny fluctuation, just a brain, than a huge fluctuation, an entire universe. So the fact that we see a large, coherent universe with a consistent history suggests that we're not a random fluctuation. We have a genuine low entropy beginning. Another possibility is that the laws of physics themselves are time asymmetric at a fundamental level. Maybe there's a tiny, tiny violation of time reversal symmetry that we haven't detected yet. We know that the weak nuclear force violates parity, mirror symmetry, and CP symmetry, charge parity symmetry. It also violates T symmetry, time reversal symmetry, just a little bit. But these violations are far too small to explain the macroscopic arrow of time. They're like a single grain of sand trying to move a mountain. The arrow of time is overwhelmingly a consequence of entropy, not of fundamental T violation. Let's think about the expansion of the universe again, because it's so important. The universe is not just spreading out, it's accelerating. Dark energy is pushing everything apart faster and faster. It's creating more space, more room for entropy to increase. It's like the box we're in is getting bigger, so the gas molecules have even more ways to be disordered. If the universe were contracting, would time run backward? Some early cosmologists thought so, but it's not that simple. A contracting universe would still have increasing entropy, at least until very near the end. The arrow of time is tied to the entropy gradient, not directly to expansion. However, the fact that the universe is expanding and accelerating makes the arrow seem permanent. It stretches out the gradient over a larger and larger volume, making it harder and harder for entropy to ever decrease. Now let's explore some more exotic ideas. What if time is discrete? What if it's not continuous, but comes in little chunks, like frames in a movie? Some theories of quantum gravity, like loop quantum gravity, suggest that space-time itself is quantized. There are minimal units of time and space. If time is discrete, then the arrow might be built into the direction of these discrete steps. But this doesn't really solve the problem. It just pushes it down to a more fundamental level. Why do the steps go forward and not backward?
What about the idea that the arrow of time is linked to the arrow of causality and the arrow of information? Maybe information can only be created, not destroyed. This is related to the black hole information paradox. If information is preserved, then entropy can't decrease, because decreasing entropy would mean gaining information about the microstate, which would violate unitarity in quantum mechanics. So the quantum mechanical principle of unitarity, the idea that probabilities always sum to 1, that information is conserved, might be the ultimate source of the arrow of time. But unitarity is time-symmetric. It works forward and backward. So again, we need an initial condition. We need the past hypothesis.
Let's talk about some specific numbers because numbers make things real. The entropy of the early universe right after the Big Bang has been calculated by Roger Penrose and others. It's about 10 to the 88 in natural units. That's a 1 followed by 88 zeros. The maximum possible entropy of the observable universe, if you turned it into a black hole, would be about 10 to the 120. So we started at 10 to the 88 and we're heading toward 10 to the 120. That's a huge increase. But here's the crazy part. The probability of starting at 10 to the 88 by random chance is 1 in 10 to the 10 to the 88th. That's a number so large that if you wrote it out, if you wrote a 0 on every single particle in the observable universe, you still wouldn't have enough particles to write it. The improbability of our low entropy beginning is so vast that it's almost meaningless. It's not just unlikely, it's absurdly, unbelievably, incomprehensibly unlikely. So either there's a reason for it, inflation, a multiverse, a fundamental law, or we're just incredibly lucky. And lucky doesn't feel very scientific. Let's explore inflation in more detail because it's our best bet for explaining the past hypothesis. Inflation theory says that the universe underwent a period of exponential expansion driven by a scalar field called the inflaton. This field had a lot of potential energy, which acted like a cosmological constant, causing rapid expansion. As it expanded, quantum fluctuations in the field were stretched to cosmic scales, becoming the seeds of structure. When inflation ended, the inflaton field decayed, releasing its energy as particles and radiation, and the universe reheated. This created the hot, dense, but still very smooth state that we call the Big Bang. So, inflation takes a tiny, possibly chaotic region of spacetime and blows it up into a huge, smooth, low-entropy universe. It explains the flatness, the uniformity, and the origin of structure. But it doesn't explain why inflation started. Was it a random fluctuation? Was it triggered by some prior state? This is the question of the initial conditions of inflation. Some theories suggest that inflation is eternal. Once it starts, it never stops everywhere. It keeps creating new bubble universes. Each bubble is a low-entropy region, but the overall multiverse is high entropy. So the arrow of time in each bubble is local. It's like having a refrigerator in a hot room. Inside the fridge, it's cold and ordered. Outside, it's hot and chaotic. The fridge creates a local low-entropy region, but it does work, it uses energy, and it increases the total entropy of the room. So inflation might be like that. It creates low-entropy bubbles, but the overall multiverse entropy increases. So the arrow of time is a local phenomenon in a sea of timeless chaos. But wait, what about the psychological arrow? We haven't fully explored that. Let's do a deep dive into how our brains create the sensation of time. Your brain is a prediction machine. It's constantly taking in sensory data and building a model of the world. It uses memory to store past data and uses that data to predict the future. This process is inherently directional. You can't predict the past because you already have data about it. You can only predict the future because it's unknown. The brain's predictive processing creates a sense of temporal flow. You experience the present as the moment where prediction meets reality. When your prediction matches what happens, you feel like you understand the world. When it doesn't, you learn, you update your model, and you store a new memory. This learning process is irreversible. It increases the information in your brain, which is a local decrease in entropy, but it does so by increasing the entropy of the environment even more. So your brain is an entropy exporting machine. It sucks in order from the environment, food, sensory data, and excretes disorder, heat, waste, random neural noise. This is why living things are called dissipative structures. They maintain order by dissipating entropy. Let's think about a specific example, reading this script. Your eyes are scanning the text, converting photons into electrical signals, sending them to your brain. Your brain is processing these symbols, extracting meaning, building a mental model of the concepts I'm describing. This process consumes glucose, produces heat, and creates memories. Every second you spend watching this video, your brain is creating order at the expense of increasing the universe's entropy. You're literally thinking the universe into disorder. That's a pretty profound thought, isn't it? Your consciousness, your ability to understand these ideas, is directly tied to the thermodynamic arrow. If the arrow reversed, you would unlearn everything. Memories would dissolve. Understanding would fade. You would become less informed, not more. Now let's talk about the arrow of time in quantum mechanics again, but this time let's get into the weeds. The Schrödinger equation is time reversible, but the process of measurement is not. This is the measurement problem. In the Copenhagen interpretation, the wave function collapses randomly when observed. This collapse is irreversible. It creates a definite outcome from a superposition of possibilities. But what counts as an observer? Does it have to be a conscious being? Most physicists think no. Decoherence, the interaction with a macroscopic environment, is enough. When a quantum system interacts with the environment, the phases of its wave function get scrambled. The superposition becomes entangled with the environment, and the interference effects that make quantum mechanics weird disappear. This process is effectively irreversible because the information about the phases leaks into the environment and gets lost in the high-entropy background. So the quantum arrow of time is really just the thermodynamic arrow in quantum clothing. But there's another quantum arrow, the arrow of radiation. When you wiggle a charge, it produces electromagnetic waves that travel outward at the speed of light. You see this as ripples in the electromagnetic field spreading into the future. They don't converge from the future onto the charge. Why not? The equations allow both solutions, outgoing waves and incoming waves. But incoming waves would require perfectly coordinated conditions from all over the universe, converging at just the right moment. That's incredibly improbable. So the arrow of radiation is also a statistical arrow. It's about boundary conditions. We impose the condition that there are no incoming waves from infinity, and that gives us the retarded or outgoing solutions. This is called the Sommerfeld radiation condition. It's an initial condition, just like the past hypothesis. So even the flow of light is tied to entropy. Let's think about gravity for a moment. Gravity seems to create order. It pulls matter together, forming stars, galaxies, planets. Doesn't that decrease entropy? No, because as gravity pulls matter together, it releases energy. The gas heats up, radiates, and that radiation spreads out, increasing entropy overall. A star is a low-entropy object locally, but it's a huge entropy-producing machine globally. It fuses hydrogen into helium, releasing photons that travel into space and increase the universe's entropy. So gravity doesn't violate the second law, it drives it. It creates the gradients that allow entropy to increase. Without gravity, the universe would have stayed smooth and boring. Gravity is the engine of complexity, but it's also the engine of entropy production. Now, I want to address a common misconception. Entropy is not the same as chaos. Chaos is about sensitivity to initial conditions. A chaotic system can be low entropy or high entropy. The weather is chaotic, but relatively low entropy compared to the heat death. Chaos is about unpredictability, while entropy is about probability and information. A system can be perfectly predictable and still have high entropy, like a gas at uniform temperature. And a system can be chaotic and still have low entropy, like a planet's orbit. So don't confuse the two. Let's get back to the multiverse idea, because it's so compelling and so problematic. The idea of a multiverse comes from several different theories: eternal inflation, string theory, and the many worlds interpretation of quantum mechanics. Each gives a different kind of multiverse. In eternal inflation, the multiverse is a collection of bubble universes with different physical constants. In string theory, it's a landscape of possible vacuum states, each corresponding to a different universe.
In many worlds, it's a branching structure where every quantum measurement creates new universes. The question is, can any of these explain the low entropy beginning? The eternal inflation multiverse seems promising. It says that inflation is constantly creating low entropy bubbles. But as we saw, it runs into the Boltzmann brain. The many worlds multiverse doesn't help, because each branch has the same initial condition as the parent universe, so it doesn't explain why the parent universe started low entropy. The string theory landscape is similar to eternal inflation. It gives you a multiverse, but you still need a mechanism to populate it with low entropy universes. So we're left with the past hypothesis as the most parsimonious explanation. The universe just started that way. It's an initial condition. It's a brute fact. But that feels incomplete. It feels like there should be a deeper principle. Maybe it's a law of physics that we haven't discovered yet. Maybe it's a consequence of quantum gravity. Maybe it's a selection effect from a mathematical ensemble of all possible universes. This is where physics meets philosophy. We start asking questions that might be beyond empirical testability, but that doesn't mean they're not worth asking. Let's explore some of these deeper principles. One idea is the principle of indifference. If you have no reason to prefer any particular state, you should assume all states are equally likely. But this doesn't work for the universe, because the universe is not a random sample of all possible states. It's a dynamical system, evolving according to laws. So we need a dynamical principle that selects for low entropy beginnings. Some have suggested that the universe is a computational system, and low entropy states are more computable or have some other information-theoretic property, but this is highly speculative. Another idea is that causality itself is fundamental, and causality requires a direction. You can't have cause without effect preceding it. But as we saw, causality is also derived from entropy, so this doesn't help. What about the arrow of time in black holes? When matter falls into a black hole, it seems to be lost forever. But if black holes evaporate, where does the information go? Some physicists, like Leonard Susskind, propose the holographic principle. This says that all the information in a volume of space is encoded on its boundary. For a black hole, the boundary is the event horizon. The entropy of the black hole is proportional to the area of the horizon, not its volume. This suggests that space-time itself is emergent from some underlying quantum information theory. And in this theory, the arrow of time might be a direction in the space of quantum information. It might be about how information becomes more entangled, more scrambled over time. This is the idea of entanglement entropy. As systems evolve, they become more entangled with their environment, and this entanglement entropy always increases. So maybe the fundamental arrow is quantum entanglement.
Let's dig into entanglement entropy. When two particles are entangled, measuring one instantly affects the other. But as they interact with the environment, they become entangled with more and more particles. The entanglement spreads, and the original entanglement is diluted. This process is irreversible. It's like dropping ink into water. At first, you have a concentrated drop. Then it spreads out, becoming uniformly distributed. You can't unmix it. Entanglement entropy measures how spread out the quantum correlations are, and it always increases. This is a quantum version of the second law. It's more fundamental than thermal entropy because it applies even at zero temperature. So maybe the arrow of time is fundamentally quantum. But here's the catch. Entanglement entropy also depends on initial conditions. If you start with a pure state, a state with zero entanglement entropy, and let it evolve, it will entangle and increase entropy. But if you start with a mixed state, you could see it decrease. So again, we need the past hypothesis. We need to start with a low entanglement state. The early universe must have been in a pure, unentangled state. Why? Because it was small.
it had fewer degrees of freedom. It had fewer particles to entangle. As it expanded, it had more room, more particles, more ways to become entangled. So the cosmological arrow drives the quantum arrow. Let's talk about the arrow of time in different physical theories. In classical mechanics, the equations are time reversible. In quantum mechanics, the Schrödinger equation is time reversible. In general relativity, Einstein's equations are time reversible. In all these theories, you can replace t with negative t and get a valid solution, so none of them have a built-in arrow. The arrow always comes from boundary conditions. In cosmology, it's the past hypothesis. In electrodynamics, it's the Sommerfeld condition. In thermodynamics, it's the low entropy initial state. So the arrow of time is not in the laws, it's in the setup. This is a profound realization. It means that the distinction between past and future is not fundamental to the laws of physics, but it is fundamental to our experience. The universe is like a movie that can be played forward or backward, but the beginning of the movie is a special frame. It's not random, it's ordered. And that order sets the direction for the rest of the film. The rest of the film is just the unfolding of that initial order into disorder. Now, let's think about the implications for our lives. If the arrow of time is just entropy, does that mean free will is an illusion? If the universe is deterministic, if the laws of physics fix everything, then the future is already written. The increase in entropy doesn't create new possibilities, it just makes them more probable. But here's the thing. Even in a deterministic universe, we don't know the future. We can't compute it. The universe is too complex, too chaotic. So from our perspective, the future is open. We make choices, we act, and we influence the flow of entropy. We create local order, buildings, computers, societies, by exporting entropy to the environment. So free will and the arrow of time are compatible. We experience time as flowing because we are part of the flow. We're not outside observers, we're participants. Let's talk about memory again, because it's so central. Memory is a record of the past. But what makes something a record? It's that the state of the record is correlated with a past event. A photograph is correlated with the light that hit the camera. A fossil is correlated with the organism that died. But these correlations are always formed in the direction of increasing entropy. You can't have a memory of the future because the future hasn't influenced the present yet. The present influences the future. So memory is an entropy gradient detector. It works because the past is ordered and the future is not. This is why we can't remember the future. It's not a limitation of our brains, it's a limitation of causality and entropy. Now, let's get into some speculative but fun ideas. What if we could reverse the arrow of time locally? What if we could create a region of space where entropy decreases? This would be like a refrigerator for time. You'd have to pump entropy out faster than it flows in. You'd need to create a huge gradient. In principle, this is possible. You can reverse entropy locally by doing work, but you can't reverse it globally. The total entropy of the universe must increase. So you could, in theory, build a machine that makes your coffee get hotter while making something else get much colder, or making a star burn faster or something. But the cost would be enormous. You'd have to increase entropy elsewhere by a huge amount. So time reversal is possible in principle, but impossible in practice. What about traveling backward in time? If you could reverse entropy for your entire body and your spaceship, could you travel to the past? Well, general relativity allows for closed time-like curves, paths through space-time that loop back to their own past. These exist in solutions like the Gödel universe or around rotating black holes. But these solutions require exotic matter or conditions that probably don't exist in reality. And even if they did, you'd run into paradoxes, the grandfather paradox, where you kill your own grandfather before you're born.
These paradoxes suggest that time travel is impossible, or that it's limited by some principle like the chronology protection conjecture, which says that quantum effects will always prevent the formation of closed time-like curves. So the arrow of time seems protected by both thermodynamics and quantum mechanics. Let's talk about the arrow of time in biology. Life is the ultimate entropy exporting machine. A single cell is a marvel of low entropy. It maintains its structure by constantly taking in high-energy, low-entropy food and excreting high-entropy waste. It uses free energy to build complexity. But this complexity is always paid for by increasing the entropy of the environment. Evolution itself is an entropy-increasing process. Natural selection favors organisms that are better at extracting free energy and exporting entropy. So the arrow of time in biology is just a special case of the thermodynamic arrow. Life exists because the universe has a gradient. If the universe were at maximum entropy, life would be impossible. No gradients, no free energy, no life.
Now, let's think about the far, far future. Trillions of years from now, the last stars will die. The universe will be dark, but it won't be empty. There will still be black holes slowly evaporating. There will be occasional flashes of light as the last bits of matter decay. And there will be Boltzmann fluctuations, random temporary decreases in entropy. In this far future, a Boltzmann brain could pop into existence, have a thought, and then dissolve back into the void. It would have memories, but those memories would be false, random correlations. It would think it had a history, but it wouldn't. It would be a ghost in the machine of entropy. This is a bleak vision, but it's a consequence of taking the second law to its logical conclusion. But maybe the universe doesn't end in heat death. Maybe there's a big rip where dark energy tears everything apart, including atoms. Or maybe there's a big crunch, where the universe collapses back into a singularity. In a big crunch, entropy would still increase until the very end. The contraction phase would be a mirror of the expansion, but with increasing entropy. So the arrow would still point forward toward the crunch. But if the universe bounced and started expanding again, would the arrow reverse? Some cyclic models suggest that each bounce resets entropy, but we don't know the physics of the bounce. It's pure speculation. Let's talk about the arrow of time in cosmology more formally. The universe has three main arrows: the thermodynamic arrow, entropy, the cosmological arrow, expansion, and the radiative arrow, outgoing waves. These arrows all point in the same direction. Roger Penrose has argued that this alignment is not a coincidence. He proposes the Weyl curvature hypothesis, which says that the initial singularity of the Big Bang had very low Weyl curvature, a measure of gravitational distortion, while any final singularities, like black holes, have high Weyl curvature. This gives a geometric distinction between past and future, and it explains the low entropy beginning. But it's still a hypothesis, not a derived law. Let's dig into Penrose's idea more. In general relativity, the curvature of spacetime is described by the Riemann tensor. This can be split into two parts: the Ricci curvature, which is tied to matter, and the Weyl curvature, which describes gravitational waves and tidal distortions. At the Big Bang, the Weyl curvature was zero, or very close to it. The universe was smooth. At a black hole singularity, the Weyl curvature diverges. It's infinite. So Penrose is saying that the geometry of the initial state is special. It's constrained. And this constraint is what gives us low entropy. But why was the Weyl curvature zero? That's the same as asking why the universe was smooth. It's the past hypothesis again. Now, let's think about the arrow of time in terms of symmetry breaking. The laws of physics have many symmetries.
They're symmetric under rotations, under translations in space and time, under various particle exchanges. But the universe we observe has many broken symmetries. The direction of time is one of them. This symmetry breaking happened at the Big Bang. The universe chose a direction. But why? Symmetry breaking usually happens when a system cools. As the universe expanded and cooled, symmetries broke. Electroweak symmetry, chiral symmetry, etc. Maybe the time reversal symmetry also broke at some phase transition. But this would require new physics, new particles, new fields. There's no evidence for this, but it's a possibility. What about the arrow of time in string theory? String theory proposes that the fundamental building blocks of the universe are one-dimensional strings, not point particles. It lives in 10 or 11 dimensions. The extra dimensions are compactified, rolled up into tiny shapes called Calabi-Yau manifolds. The shape of these manifolds determines the laws of physics in our four-dimensional world. Could the arrow of time be encoded in the geometry of these extra dimensions? Maybe the compactification process is irreversible. Maybe the shape of the extra dimensions determines an entropy gradient. This is highly speculative, but string theorists have considered it. The problem is that string theory doesn't make unique predictions. There are something like 10 to the 500 possible Calabi-Yau manifolds, each giving a different universe. So we're back to the multiverse and the anthropic principle. Let's talk about the arrow of time and the holographic principle again, because it's so important. The holographic principle says that the information content of a region of space is proportional to its surface area, not its volume. This suggests that space-time is emergent. The real physics happens on the boundary, and on the boundary there's a quantum field theory without gravity. In this theory, time might be different. It might be emergent from entanglement. There's a conjecture called ER equals EPR, which says that entangled particles are connected by wormholes, Einstein-Rosen bridges. This suggests that space-time itself is built from entanglement. If entanglement entropy always increases, then space-time grows and time gets an arrow. So the arrow of time might be a consequence of the growth of entanglement in the holographic boundary. This is cutting-edge stuff, and it's not proven, but it's a beautiful idea. It unifies quantum mechanics, gravity, and thermodynamics. Now, let's think about the arrow of time in the context of the simulation hypothesis. If we're living in a computer simulation, the arrow of time is just the direction of the computation. The simulation runs forward, one tick at a time. It computes the next state from the previous state. This is inherently directional. You could run the simulation backward, but that would be a different computation. The laws of the simulation are reversible, but the computation is not. The initial state is special. So the simulation hypothesis doesn't solve the problem, it just reframes it. Why did the simulators choose a low entropy initial state? Because they wanted to see interesting things evolve. They wanted to see stars, galaxies, life. So they set up the initial conditions to allow for an arrow of time. It's the same as the anthropic principle, but with programmers instead of physics.
Let's get back to basics and really hammer home the connection between entropy and probability. Imagine you have a box with a partition. On one side you have red balls, on the other blue balls. That's low entropy. You remove the partition, the balls mix. That's high entropy. But here's a subtlety. If you track every single ball, you can reverse the mixing. You can pick up each ball and put it back. But if you only care about the color distribution, if you coarse grain, the mixing is irreversible. You can't unmix without doing work. So entropy is about what you ignore. It's about the level of description. The universe doesn't care about entropy, we do. The universe just evolves according to its microscopic laws, but because we don't know the exact micro state, we use probability, and that gives us entropy.
So the arrow of time is a feature of our description of the universe, not the universe itself. But it's a necessary feature. Any finite observer has to coarse grain. Any finite observer will see an arrow. Now let's think about the arrow of time in the context of the many worlds interpretation. In many worlds, the wave function never collapses. It just branches. Each branch is a separate world. In each world, entropy increases, but the overall wave function is unitary and reversible. So from the perspective of the entire multiverse, there is no arrow. The arrow is only in each branch. This is mind-bending. It suggests that the arrow of time is a subjective feature of a branch, not an objective feature of reality. But each branch is real, so the arrow is real to each observer in each branch. It's a relative concept. Let's talk about the arrow of time and the concept of now. What is now? It's the present moment. But in physics, there's no special now. In the block universe, all times are equally real. Now is just a slice through space-time that we label as present. Different observers moving at different velocities have different nows. This is relativity of simultaneity. So now is subjective. It's like here. You have a here, I have a here. They're different points in space. Similarly, you have a now, I have a now. They're different points in time. But we both experience time flowing. Why? Because we both have memory. We both have a psychological arrow. So now is the moment where our memory meets our perception. It's the edge of our knowledge. Let's explore the psychological arrow more deeply. How does the brain create the sensation of a continuous now? It's not a single moment, it's a process. The brain integrates sensory input over a short window, maybe a few hundred milliseconds. It stitches together a coherent narrative from this input. It also uses memory to give context, so your experience of now is actually a smeared-out, constructed experience. It's not a point, it's an interval. And it's always moving forward because new sensory input is always arriving, and old input is being stored as memory. This is a computational arrow. It's about processing, and processing takes energy, which increases entropy. So the psychological arrow is built on the thermodynamic arrow. Now let's think about the arrow of time in the context of life and death. Birth is a low entropy event. A baby is highly ordered. Death is a high entropy event. The body decays, becomes disordered. Life is a struggle against entropy. We eat, we breathe, we repair our cells, all to maintain order. But we can't win. Eventually, entropy catches up. This is the personal arrow of time. It's the most poignant arrow. We feel it in our bones. We see it in the mirror. And it's the same arrow that governs the stars. We're all in the same river, just at different scales. Let's talk about the arrow of time and technology. Your computer is an entropy machine. It takes electrical energy, those computations, and produces heat. The heat is the waste product. The computation is the ordered outcome. But the computation itself increases entropy. Each logic gate operation dissipates a tiny amount of heat. This is called Landauer's principle. It says that erasing a bit of information requires a minimum amount of energy, which is released as heat. So computation has a thermodynamic cost. This is why your laptop gets hot. It's why we can't have infinite computation. It's why there's a fundamental limit to how powerful computers can be. The arrow of time limits our ability to process information. It's a fundamental constraint on technology. Now let's think about the arrow of time in the context of cause and effect in everyday life. You drop a glass, it shatters. The cause is dropping, the effect is shattering. But why can't the shattering cause the dropping? Because the shattering is more disordered. It has higher entropy. The cause is the low entropy event. The effect is the high entropy event. This is a general principle. Causes have lower entropy than effects. This is why we can control causes, but not effects. We can choose to drop the glass, but we can't choose to make it shatter and then have that cause us to drop it. So causality is entropy-driven. It's a statistical principle. It's not fundamental to the laws, but it's fundamental to our ability to act in the world. Let's explore the arrow of time in the context of the universe's ultimate fate. We talked about heat death, but there's also the Big Rip, where dark energy tears everything apart.
In the Big Rip, the expansion accelerates so fast that eventually galaxies are pulled apart, then stars, then planets, then atoms, then nuclei. The universe ends in a singularity of infinite expansion. In this scenario, entropy still increases. The arrow points to the rip. There's also the Big Crunch, where the universe collapses. In that case, entropy increases until the final moment. There's no reversal. The arrow points to the crunch. And there's also the vacuum decay scenario, where the universe tunnels to a lower energy vacuum state, creating a bubble of new physics that expands at the speed of light, destroying everything in its path. In that case, entropy might reset inside the bubble, but outside, it's still increasing. So no matter the fate, the arrow seems to persist.
Now let's talk about the arrow of time and the concept of reversibility in physics. We said classical mechanics is reversible. If you know the positions and velocities of all particles at one instant, you can calculate them at any past or future instant. But this is an idealization. In practice, you can't know all the microstates. You coarse grain. And that coarse graining introduces irreversibility. It's like trying to unmix ink from water. In principle, if you knew the exact position and momentum of every ink molecule, you could reverse the diffusion. But in practice, you can't. The information is lost in the chaos. So reversibility is a property of the microscopic description, while irreversibility is a property of the macroscopic description. The arrow of time lives in the macroscopic world. Let's think about the arrow of time and the concept of information loss. When entropy increases, information is lost. But is it really lost or just inaccessible? In principle, the information is still there, encoded in the microstates. But we can't access it without doing work, without decreasing entropy elsewhere. So information is effectively lost. This is the connection between entropy and information theory. Claude Shannon, the father of information theory, defined entropy as a measure of uncertainty. The more uncertain you are about a message, the higher its entropy. So when a system evolves to a higher entropy state, you're more uncertain about its microstate. You've lost information. This is why the second law is sometimes called the law of information loss. Now let's talk about the arrow of time in the context of the initial singularity. The Big Bang is a singularity, a point of infinity density where physics breaks down. Some theories, like loop quantum gravity, suggest that the singularity is resolved. There's a bounce from a previous universe. But even if there was a previous universe, we still need to explain why the entropy was low at the bounce. The bounce itself might be a low entropy event. It might be a resetting of the entropy clock. But why? What physics would allow that? We don't know. Let's explore the arrow of time and the concept of time crystals. A time crystal is a system that oscillates in time without any external input. It breaks time translation symmetry. It has a periodic structure in time, like a crystal has a periodic structure in space. Time crystals have been created in the lab. They seem to be stable, persistent oscillations. But do they have an arrow? No, because they're periodic. They don't have a direction. They just loop. So time crystals are an interesting exception to the arrow, but they don't violate the second law because they're isolated systems that don't increase entropy. They're like a pendulum that never stops. But in reality, they will eventually decohere and stop, increasing entropy. Let's talk about the arrow of time and the arrow of life. As we said, life is a low entropy structure. It maintains order by exporting entropy. But life also creates information. DNA is a low-entropy information storage system. It encodes the instructions for building an organism. The evolution of life is a process of increasing complexity, which seems to be a local decrease in entropy. But it's paid for by the entropy increase of the sun, which powers life. So the biosphere is a dissipative structure. It's a pattern that persists because it flows energy through it. This is the key to understanding life in the context of the arrow. Life is a vortex in the river of entropy. It maintains its shape by constantly moving energy through it. Now let's think about the arrow of time and the arrow of consciousness. Consciousness is the most mysterious arrow. We feel time passing. We feel the now. We remember the past and anticipate the future. Is this just computation? Is it just memory, or is there something more? Some philosophers think consciousness is fundamental and it creates time. Others think it's emergent and it's a byproduct of the thermodynamic arrow. We don't know. But what we do know is that consciousness requires a brain, and a brain requires low entropy. So consciousness is contingent on the arrow. Without the arrow, there would be no thought. Let's explore the arrow of time in the context of artificial intelligence. An AI is also a dissipative structure. It runs on computers, which increase entropy. It processes information, which has a thermodynamic cost. If we ever create a conscious AI, it will also experience an arrow of time. It will have memory, it will learn, it will have a sense of past and future. And that arrow will be the same as ours, because it's the same universe. So the arrow is universal for any information processing system. Let's talk about the arrow of time and the arrow of history. Human history is a record of entropy increase. We build civilizations, which are ordered, but we do so by burning fossil fuels, increasing entropy. Wars destroy order, increasing entropy. Technological progress creates order, but at a cost. So history is just another manifestation of the thermodynamic arrow. It's the story of how the universe's low entropy beginning gave rise to complexity, and how that complexity will eventually fade. Now let's think about the arrow of time and the arrow of creativity. Creativity is the creation of new information, new patterns. It's a local decrease in entropy, but it's fueled by inspiration, which comes from the chaotic, high-entropy environment. So creativity is a dance with entropy. It uses disorder to create order. This is why creative blocks feel like being stuck in entropy. You can't find the new pattern. And when you create, you feel like you're riding the arrow, you're moving with time. Let's talk about the arrow of time and the arrow of emotion. Emotions are temporal. Grief is about the past, anxiety is about the future, joy is in the present. Our emotional lives are structured by the arrow. We feel loss because the past is gone. We feel hope because the future is open. This is deeply tied to memory and anticipation, which are entropy-driven. So our very feelings are shaped by the arrow. Now let's get back to physics and really nail down the relationship between the cosmological arrow and the thermodynamic arrow. The universe is expanding. This expansion creates room for entropy to increase. If the universe were static, entropy would still increase, but it would reach equilibrium. The expansion pushes equilibrium further away. It's like the goalposts are moving. The universe is constantly making more room for disorder. This is why the arrow seems so persistent. It's not just a local gradient, it's a cosmic gradient that's being reinforced by expansion.
But what if dark energy changes? What if the acceleration stops and the universe starts contracting? Would the arrow reverse? Probably not. The contraction would still involve increasing entropy. The arrow is tied to the entropy gradient, not the expansion rate. But if the contraction led to a big crunch, and that crunch bounced to a new expansion, could the arrow reverse in the new cycle? Some cyclic models suggest that the arrow reverses after the bounce, but this is pure speculation. The physics of the bounce is unknown. It might be that the arrow always points in the same direction, cycle after cycle. Or it might be that each cycle has its own arrow, independent of the previous one. We just don't know. Let's talk about the arrow of time and the arrow of quantum measurement. In the de Broglie-Bohm interpretation of quantum mechanics, particles have definite positions, guided by a wave function. The wave function never collapses. In this theory, the arrow of time is explicit. The wave function evolves and the particles follow. But it's still reversible at the fundamental level, so we still need the past hypothesis. Now let's think about the arrow of time and the arrow of space-time geometry. In general relativity, space-time is dynamic. It can be curved, it can ripple, it can expand. The geometry of space-time is determined by the distribution of matter and energy. In the early universe, the geometry was very simple, very symmetric. As the universe evolved, it became more complex, more structured. This is a kind of geometric entropy. The shape of space-time itself has an arrow. This is related to Penrose's Weyl curvature hypothesis. The geometry was simple then, it's complex now.
It will be simple again at the heat death when everything is uniform. So the arrow is a journey from simple geometry to complex geometry back to simple geometry. But the complexity is where life happens. Let's talk about the arrow of time and the arrow of cosmic structure. Galaxies, stars, planets, these are all intermediate entropy structures. They form because gravity pulls matter together, but they shine because nuclear fusion releases energy. The energy flows from hot cores to cold space, increasing entropy. So, cosmic structure is a manifestation of the arrow. It's the universe's way of increasing entropy as fast as possible. Some physicists think that the universe evolves to maximize entropy production. Life is part of this process. We burn fuel, we create waste, we increase entropy. So the arrow is not just a passive unfolding, it's an active process of entropy maximization. Now let's think about the arrow of time and the arrow of quantum fields. In quantum field theory, fields fill space. They can be in excited states, particles, or ground states, vacuum. The early universe had fields in excited states, but they were uniform. As the universe expanded, the fields could form localized excitations, particles, clumps, structures. This is a kind of field entropy. The arrow is the evolution from uniform fields to clumpy fields. This is what created matter as we know it. Let's explore the arrow of time in the context of symmetry breaking. The early universe was symmetric. All forces were unified. As it cooled, symmetries broke. The electroweak force split into electromagnetism and the weak force. This symmetry breaking created mass, created particles, created structure. Each symmetry breaking is an irreversible event. It increases entropy. So the arrow is a record of broken symmetries. The universe is less symmetric now than it was at the beginning, and it will become even less symmetric in the future as it spreads out. Now let's think about the arrow of time and the arrow of consciousness again, but this time let's get philosophical. The philosopher David Chalmers talks about the hard problem of consciousness. Why do we have subjective experience at all? Could the arrow of time be related? Maybe consciousness is the universe's way of experiencing its own entropy increase. Maybe we are the universe's memory. This is a poetic idea, but it's not scientific. Still, it's worth pondering. If the universe has no observers, does the arrow still exist? Physics says yes, because the entropy gradient exists. But would it matter? Without observers, there's no one to remember the past, no one to anticipate the future. The arrow would be unexperienced. So in a sense, consciousness gives meaning to the arrow. Let's talk about the arrow of time and the arrow of meaning. Meaning is temporal. It requires a past, a present, and a future. A story has a beginning, middle, and end. Without the arrow, there are no stories. So the arrow of time is what makes life meaningful. It's what makes it a journey, not a static picture. This is why the question, why does time only move forward, is so profound. It's not just physics, it's philosophy, it's psychology, it's meaning itself. Now let's get back to the physics and really dig into the past hypothesis. Why is it called a hypothesis? Because it's not derived, it's an assumption. We assume the universe started in a low entropy state because that's what we observe, but we don't know why. Some physicists are trying to derive it from quantum cosmology. They use the Wheeler-DeWitt equation, which describes the wave function of the universe. This equation is timeless. It doesn't have a t variable. So how do you get time from a timeless equation? You use decoherence. You split the universe into system and observer, and you get an emergent time. But this is still controversial. It's not clear that you can derive the past hypothesis without assuming it. Let's talk about the arrow of time and the arrow of quantum gravity. In quantum gravity, space-time is made of discrete loops. Time might be emergent from the dynamics of these loops. In string theory, time is a dimension like space, but it might be emergent from the boundary theory. In both cases, the arrow is not fundamental. It's a property of the emergent space-time, and it's tied to entropy. The holographic principle suggests that the arrow is a direction in the space of quantum states, a direction of increasing entanglement.
Now let's think about the arrow of time and the arrow of observation. When we observe something, we interact with it. We become entangled with it. This interaction is irreversible. It increases entropy. So the act of observation creates a record, a memory. This is why the Copenhagen interpretation says measurement collapses the wave function. The collapse is the creation of a classical record, and that record is irreversible. So the arrow of time is created by observation. But this is anthropocentric. Decoherence doesn't require a human observer, it just requires an environment. So the arrow is objective, but it's about information leakage. Let's talk about the arrow of time and the arrow of complexity. Complexity seems to increase over time. From simple particles, we get atoms, molecules, cells, organisms, and societies. Is this a law? Not exactly. Complexity can decrease locally, but it tends to increase globally because there are more ways to be complex than simple. This is similar to entropy. So the arrow of complexity is a cousin of the arrow of entropy. But complexity is not the same as entropy. A living cell is more complex than a gas, but it has lower entropy. So complexity is a different measure. It's about structure, not just disorder. But the two are related. The universe seems to evolve to create complex structures that increase entropy faster. Life is the ultimate example. A planet with life increases entropy faster than a dead planet. So the arrow of time is also an arrow of complexity. Now let's think about the arrow of time and the arrow of cosmic evolution. The universe started simple, got complex, and will end simple. This is a U-shaped curve of complexity. The arrow is the upward slope. It's the part where interesting things happen. So the arrow is not just about disorder. It's about the journey from simplicity to complexity and back. It's about the story of the universe. Let's talk about the arrow of time and the arrow of personal identity. Who are you? You're a pattern of information, a configuration of atoms that persists over time. But that pattern is constantly changing. You're not the same person you were 10 years ago. Your atoms have been replaced, your memories have changed, yet you feel like a continuous self. Why? Because you have memory. You have a narrative. The arrow of time gives you identity. Without it, you'd be a static pattern, not a person. So the arrow is what makes you you. Now let's think about the arrow of time and the arrow of love. Love is temporal. It grows, it fades, it leaves memories. It's a process, not a state. It requires time. So the arrow gives love its poignancy. It's what makes it precious. Without the arrow, love would be eternal and meaningless. With the arrow, it's fleeting and profound. Let's get back to physics and really nail down the arrow of time in the context of the initial state of the universe. The initial state is described by the cosmic microwave background, CMB. This is the afterglow of the Big Bang. It's incredibly uniform, but it has tiny fluctuations, 1 part in 100,000. Those fluctuations are the seeds of structure. They are low entropy variations. They are the reason we exist. If the CMB were perfectly uniform, there would be no galaxies, no stars, no us. So the CMB is the observational evidence for the past hypothesis. It shows us the low entropy initial conditions, and it's incredibly precise. The temperature is 2.72548 Kelvin, and it's the same in all directions to within 0.001%. That's the low entropy state, and those tiny fluctuations are the key to everything. Let's talk about the arrow of time and the arrow of structure formation. Those tiny fluctuations in the CMB were amplified by gravity. Dense regions got denser, forming clumps, then galaxies, then stars. This is a process of gravitational instability. It's an entropy-increasing process because the gas heats up, radiates, and spreads out energy. So structure formation is entropy-driven. The universe makes stars because stars are good at increasing entropy. They shine, they spread light, they enrich the universe with heavy elements that can form planets and life, which increase entropy even more. So the arrow is a creative force. It builds the structures that accelerate entropy production. Now let's think about the arrow of time and the arrow of nuclear fusion. Stars fuse hydrogen into helium, releasing energy. This is a nuclear reaction that increases entropy. Helium has less nuclear binding energy than hydrogen, so the difference is released as heat and light. This is the engine of the universe. It powers life. And it's irreversible. You can't fuse helium back into hydrogen without putting in more energy than you got out. So, fusion is an entropy arrow. It points from hydrogen to helium to heavier elements, all the way to iron, which has the most binding energy.
After iron, fusion doesn't release energy, it absorbs it. So the arrow stops at iron. That's the end of the line for nuclear entropy production. Let's talk about the arrow of time and the arrow of chemical reactions. Chemistry is all about entropy. Reactions proceed in the direction that increases entropy. You mix chemicals, they react, they release heat, they form products that are more disordered. But life uses chemistry to create order. Enzymes catalyze reactions that build complex molecules, but these reactions are coupled to other reactions that increase entropy overall. So metabolism is an entropy exporting process. Life is a chemical miracle that rides the arrow.
Now, let's bring this all together. The arrow of time is not one thing, it's many things. It's the thermodynamic arrow of entropy. It's the cosmological arrow of expansion. It's the radiative arrow of outgoing waves. It's the quantum arrow of decoherence. It's the psychological arrow of memory. It's the biological arrow of life and death. It's the social arrow of history and culture. It's the personal arrow of growth and aging. All these arrows point the same way because they are all manifestations of the same underlying principle. The universe started in an incredibly improbable low-entropy state, and it's been unwinding ever since. We are the universe's way of knowing itself, of experiencing its own unfolding. We are temporary patterns in the flow, low-entropy islands in a sea of increasing disorder. And that's okay. That's what makes us precious. The arrow gives us meaning, direction, purpose. It gives us life, love, loss, hope. It gives us everything. So, when you look at your coffee getting cold, remember, you're not just seeing heat dissipate. You're seeing the universe tell its story. You're seeing time itself in action. You're seeing the reason you exist. And that's pretty amazing for a cup of coffee. Now, before we wrap up, I want to ask you again, if you've made it this far, if your brain is buzzing with these ideas, if you're seeing the world a little differently now, please hit that like button. It means the world to me. And if you haven't subscribed yet, what are you waiting for? We've got so many more mind-bending journeys ahead. And seriously, drop a comment. Tell me where you are, what time it is, and what you thought of all this. Are you in a bustling city where the arrow feels fast? Are you in a quiet place where it feels slow? Are you watching this at dawn when the world is fresh and low entropy? Or at midnight when everything feels like it's winding down? I read every comment and I love hearing from you. We're all in this together, riding the same arrow, and it's nice to know we're not alone. And now, as we reach the end of our journey through time, I want to say thank you. Thank you for spending this time with me, for letting me share these ideas, for being curious about the universe. Remember, every moment is precious. Every second is a gift of low entropy that won't last, so make the most of it. Learn, love, create, explore. Ride the arrow with grace and wonder. Goodbye, my friends. Good night. May your dreams be full of patterns, and may tomorrow bring you new moments of beautiful, fleeting order. Take care.